both of the bottoms. Same exact story, except I'm using that LCD that I erased. And I'm saying, okay, on this first one, I need this whole thing down here, right? So I have to multiply this here and here, both places. When I multiply x times this is where I get the x squared times the 2 minus x. Are you following me or no? You sure? That looks like a nod of just...
Yes and no.
Okay. Okay, so if it's been a while, that's kind of why we're reviewing, because we want to be comfortable with this, and if you're not, you just need to go back and practice to the point where it gets comfortable. Because calculus, I don't think I've mentioned this to you yet, you know, calculus is really, I've always said it's algebra on steroids. I mean, it's really, the algebra in calculus is challenging. So this stuff, these little things like just getting common denominators between rational, this is a rational expression, just being able to get a common denominator and group things together, you just have to be comfortable with that, or else later on, you know, you're going to be, what do they call, one-legged man in an ass-kicking contest, right? I mean, it's that sort of thing. It's what are you going to do? You know, you're going to be, was that politically incorrect? I'm sorry if it was. I don't mean to offend anyone. I'm trying to make a point, right? So if you're hung up on this, just you need to be aware of it and try and get yourself up to speed. It means go do and practice more of these problems. Okay, so now I'm going to combine these together. Just distribute this through. So we get 2x squared minus x cubed plus the 2 minus the x. And be careful here because the minus goes to both. So it's what? Minus x squared plus x, good. And then all of that over the common denominator. And collect like terms. Negative x cubed, that takes care of this. X squareds, I only have one of them, because 2x squared, take away x squared. X's, how about x's?
It takes away.
Yeah, they're gone, right? And then all you're left with plus 2 over your common. So that expression is equivalent to the original one right here. It's just as a single expression instead of 3 different expressions. It's just an exercise in algebra. That's all that was. If someone told you to subtract these two, you could write that down. That would be just as correct as this is. But we want to just manipulate, be able to manipulate things and not freak out too much. All right. Going to do 1.2.7. Have you ever heard that expression, divide and conquer? You know, the idea behind that expression, divide and conquer, is that you have a big problem, right? And instead of trying to attack this big problem, you split it up into smaller problems, and you just kind of go at each smaller problem. They seem like more reasonable tasks if you do it that way, right? Well, in calculus, we're going to have some problems that appear to be very big, and we are going to kind of divide and conquer. So we are going to take something like capital M of x equals sine to the 5th of x squared plus 1. And we are going to be asked to take this kind of ugly looking function and write it. It says find, sorry, let me get to this so you can follow along. I should have been doing this to begin with. There we go. It's this one right here. Given capital M of x is sine to the 5th, x squared plus 1. Find the functions f, g, and h such that capital M of x is equal to f of g of h of x. This is called decomposing functions. It's the opposite of what we just did. Previous one, I gave you two functions, I asked you to compose them. Now I'm giving you one big function, I'm asking you to decompose them. So what I need to do is I need to be able to write this where m of x is equal to some function f composed with some function g composed with some function h. If I can get that to work out, then I have successfully decomposed it. And we'll talk about why that would be useful in a minute. So how many layers are there? How many layers am I asked to find here? There's three layers. So I want to try and see if I can look at capital M as being a three-layered function. You have an outer layer, a middle layer, and an inner layer. And I always like to start with the outer layer and work my way in. But some students can see it easier if they start from the in and work their way out. It just depends on you. So let me again try it from the outside in. And the way that you can figure out what the outside function is to imagine that you have to plug a number into this. If I had to plug a number into this, what would be the first thing that I would do? I would square it and then add 1 and then take the sine and then to the 5th power. So we all have to be really comfortable with the idea that that little 5 there really sits on the way outside. We just like to put it here because it saves us having to write those parentheses. So the order is that you start, the inner thing happening is this, then the next thing outside of that is the sine, then the next thing outside of that is the 5th power. So I said I like to work my way out to in. So I'll first try by defining little f, which is the outer function. And that's because it's the first one in my sequence. So remember, you go from the inside out on composition, h, then to g, then to f. So f is the outside. So what is the outer function doing? What does it do? It's basically a 5th power function. It's taking something and raising it to the 5th power. What is it taking and raising? In this case, this big ugly thing, right? But in general, all it does is take something in and raises it to the 5th. So I'm going to write f of x is x to the 5th, and that's it. That should handle that 5th power. If I plug x into this, it'll raise it to the 5th. If I plug z into this, it'll raise it to the 5th. If I plug sine of x squared plus 1 into this, it'll raise that all to the 5th. Okay, so the 5th power is done. Let's work our way in. What's the next thing inside? We have sine of something, right? Sine of whatever's in here. So it's a function that takes the sine of whatever you give it. So I can write it as g, that's my next function in, sine of x. And then, if I go one more layer in, x squared plus 1, I could just write that as the final inside function. It's a polynomial. h of x is x squared plus 1.
Is there multiple ways to write that?
In this one, it would be tough to come up with another way. But in general, you can have multiple representations. Did you have something else in mind?
Could f of x be sine to the 5th x?
Yes, but I'm concerned about what you're going to do further down. So let's see. Sine to the 5th x, all right? X squared plus 1. So I agree if I take that and plug it into here.
Just x
then
plus 1, and then h of x would be x squared.
Okay. So that would work. If g of x is x plus 1,
H of x is x.
and h of x is x squared, would that work? X squared, that would first get plugged into g. So what would that become? X squared plus 1, and then take that and plug that into this, and you got, yes? Okay. So that would work also. So there are multiple representations generally. So that, whatever you see is probably best. What the goal is going to be later, though, is to see if the functions that you've decomposed into are nice. So look at mine. X to the 5th power is a nice power function, right? X to the 5th power. We know what that looks like. I mean, like if we graph it. Sine function, we know what that looks like. And x squared plus 1, we know what that looks like. So remember the idea of divide and conquer here. If I could somehow if later on I need to deal with this ugly thing, I'm claiming that we will actually break it down into its simpler parts and attack each of those parts individually. It'll be a little bit easier for us to do. Over here, you're still going to have kind of a messy looking function in your decomposition. Even though these two are real nice, this one's still a little messy. So maybe you add one more layer onto it. Maybe you have like a q of x that you add up here. You make that your x to the 5th and take that away. And now you've broken it down. And now you have 4 functions, but they're all simple. Good question. See what time we got, 10 after. See, was there anything else here? No. Composition, sine, stretching, reflecting. Let's talk a little bit about the exponential and log functions. These are going to come into play. Remember we were talking about infinity last time? We were talking about this idea of infinity. Let's look at f of x is e to the x. The graph of this is an example of exponential growth. It has a horizontal asymptote that way, right? So what would happen if I had some expression, and again, I'm having you think infinitely right now. What would happen if I took something like e and raised it to the infinity? How would that behave? Remember, infinity is not a number, it's just this idea, right? So, what do you think that would behave like?
Like on the graph?
Well, yeah, we can connect it to the graph. That's what I'm trying to hopefully see that you'll do here.
It should just be a constant, right?
Well, infinity is not a number, though, right? The idea is that I'm taking the number e and I'm raising it to a power that keeps getting bigger and bigger and bigger.
The graph would, the line would never end.
Okay, so where is it headed, though? Like, is it headed anywhere?
Yes.
Where?
Up.
Off where? Where is that? I know where you're saying it goes, but where is it? Infinity, right? Positive or negative infinity? Positive infinity. So the way you can connect it to this graph is that when you're saying e to the infinity, what you mean is look at the graph of e, right? E to the x. Look at it. That's what e to the x looks like. As the x gets bigger, right? 1, 2, 3, 4, the actual value of the function keeps going up and up and up. So where is the graph headed? Positive infinity. So this tends to infinity. Right? Now let me ask a different question. And I'm going to ask Samuel, my tired texter over there. Right? You know the rules on texting, right? So you have to make a decision. Is that texting worth you not being capable of getting an A on the next test? If it is, like my daughter's right now having surgery done, if that were important, I would be doing that. This is more important right now. If it's worth it to you, I'm happy to take 10 points away. Also, you too. Melina and, where's yours? You were though, you were, okay? I'm not gonna make examples out of anyone this week, all right? So text away. But I will, today will be it, all right? But I'll give you a chance to redeem yourself, Samuel, because maybe you know all this is too easy. So what does this tend to? Okay, so let's see if, do we have agreement? Does that head towards negative infinity? Anyone agree? It's heading to negative infinity. Okay, anyone have another proposition here?
I want to say 0.
0?
Yeah.
Anyone agree?
Yeah.
Okay, that's it. It's heading towards 0. So, why? Again, the behavior. We're saying this is what e to the x looks like. We can see from the graph that if this number gets to be a very big negative number, we're headed this direction, aren't we? And as the graph goes out that way, it gets smaller and smaller and smaller and smaller. Headed towards 0. Doesn't actually ever get there, but it heads to 0. Just our understanding of what that graph looks like allows us to answer these two questions about the way they behave. Now, I want to show you one more thing with this that I think is pretty cool. What did we say back in college algebra? When you had something to a negative power, you could always do what with it? Drop it down, right? Like if I said, what's x to the negative 2 mean? You would say that's 1 over x squared, right? Okay, could I rewrite this as 1 over e to the positive infinity? Yeah, sure. Now tell me, what happens if I have a fraction? The top is 1 and the bottom is getting, you just told me the bottom's getting huge. What does that go to? 0. And it gives you the same result, doesn't it? Two ways of looking at it. One of them requires kind of a graph. The other one requires just an understanding of how numbers are working. One gets huge, the other one's not moving. So the bottom blows up, the fraction goes to nothing. We talked about this last time, right? This is going to be a common theme throughout the course, so I'm trying to stick it anywhere I can get it in. I'm going to get it in here, okay? All right, that's e to the x. Let's try a different one. Logs, we love logs. So let's use the natural log because we like the natural log. So what do you think happens with the natural log as you plug numbers into it that are getting bigger and bigger and bigger? So I'm asking this question. What's the natural log of infinity tending towards? How is it behaving?
0.
To 0? Anyone else? 0?
It's decay,
I
right?
don't know. Yeah. I mean, I know, but you know what I'm saying. Where are you getting 0 from?
Because it's just the inverse of the exponent, so you're going to flip the graph, and it's going to be...
Is it just the inverse? I mean, it is the inverse. You said flip the graph. Flip it where, though? It looked like you flipped it over the y. Yeah, remember we said that inverse functions... Oh, wait, that was the other class. Sorry, Cal 2. Inverse functions are not flipped over y. They're flipped over...
The x.
Not the x. Y equals x. They're flipped over the diagonal. So if you look at e to the x, right, the log function should be the reflection of that over this diagonal line. I thought this was in the video. There's e to the x, right? Didn't I have natural log right there, like that? So now, what does the natural log function tend to do as you go out to infinity now that you have the picture of it? And I'll go a little further. Let me go plot range a little bit more. And I'll show the identity. There's that diagonal we were talking about. It also tends to infinity. So what's happening is that, here I'll graph the natural log here, is that there is no horizontal asymptote for the natural log. It grows, it just doesn't grow real rapidly. It's not like an e to the x. But as you move out, it keeps getting bigger and bigger, and there is no stopping it ever. So it will tend to infinity also. What about this one? This will be a tricky one. What happens if I try and put negative infinity into the natural log? How does it behave? What's that? It doesn't work, right? Because That's right, the vertical asymptote is at 0, so you actually have, it's not defined over for negative numbers, right? So this actually makes no sense for me to discuss that. This would be a domain problem, right? Some sort of domain error there. I cannot look over there, right? I cannot look that direction for the natural log. So I know that if I plug a number that gets bigger and bigger and bigger into natural log, the function will get bigger and bigger and bigger. It looks like if I try and move to the left, I can't move past 0. But what seems to be happening as I actually get closer to 0? Like, what's my graph doing as I move closer to 0? It's diving down to where? Negative infinity. So how could I say that? I could say something like this. Natural log, I can't do this. Can I? I mean, that doesn't make any sense. We should know from college algebra natural log of 0 is undefined. But if what I'm saying here is that this thing is going to 0, right? If the thing inside of here is getting smaller, that yes, the graph does start to take off towards negative infinity. Even though I can never be 0 if I get closer to it. Now we're going to like formalize this in the next section and have like actual definitions and things. I'm just trying to get your gears to think a certain way, you know, your brain to start thinking a certain way. I think that's all I want to say about natural log. All right, we've got about 20 minutes, so let's get an introduction here to the next section. And I did not ask you to watch anything on this, so we'll just take a look at it. And you know what? Can we kill the light over here on this side? I might turn the camera so we can just see this. Let's not try and go to sleep. That looks okay. Now, some of you may have watched this already, and that's a good thing. All right, so we're going to start talking about something called the limit of a function. And we have a polynomial function here. It's actually defined. Can everyone see that function, what it is? Negative x cubed plus 4x squared, and I've graphed it here. So what I want to know to start here is if we go from the left, right, from the left, the function's value appears to be approaching 8. So we're looking at the behavior of this function around the value 2. So I want you to go to the value 2 here. I want you to take a look. If you plug in 2, it looks like the value of the function is 8. Everyone agree? That's college algebra. You plug in 2, it spits out 8. What we're interested in, though, is not what's happening at 2, it's what's happening near 2. Near 2. So what I'm going to do is I'm going to approach the function from the left side. So what I'm doing is I see that dot, I'm moving it around. The blue is the value of x. This purplish looking thing is the value of y. And as I get closer and closer to the value 2, 1.6, 1.7, 1.8, whoa, went too far, 1.9, I think it's obvious, is it obvious, that it is getting closer to 8 up here? Go a little bit more. 1.9, let me go a little bit slower into it. 1.91, 1.92, 3, 4. Let me go even more refined. 1.991, 1.992. The closer I let my x value get to 2, the closer this value gets to 8. Do y'all see it? But if I'm not allowed to ever be 2, I'm never going to get to 8. right? If I can actually be 2, I can never get to 8. But I can still talk about the idea that as I get close to 2, I get close to 8. So we have this new language of close, without actually being there, getting close. Now, does it work the same way if I come in from the other side? So let me come in from the right side. So as I come in, where am I? There we go. Coming in. So what happens? What's the value of the function right here? A little bit bigger than 8? I actually go up above 8, don't I? But as I get closer to the value of x is 2, as I get closer, the y value is approaching what? It is approaching 8. This time, though, I'm a little more, though, right? I'm above it. So when I came in from the left, I was always a little bit below 8, and I was never actually going to get there. From the right side, it looks like in this function, I'm always going to be a little bit above 8. And again, it doesn't look like I'm actually ever going to get there, does it? Not if I'm not allowed to actually be 2. Get the idea? A little bit? So we have an immediate question that should go through your mind. I'm talking about being close. And close is something that's relative, right? It's a very relative word. And the analogy I like to use is, you know, if I'm standing here in this classroom, am I close to SeaWorld?
Relatively.
Relatively, right? Am I close to this stapler? Am I close to the stapler?
Yes.
Okay, then am I close to SeaWorld?
No.
Not relative to the stapler. Relative to the stapler, SeaWorld's pretty far away. If this is what I mean by close, then... So we run into this huge problem of what do we mean by close. And so there are precise definitions that we use in mathematics to get around that, and we actually define what we mean by that. But in a class like this, this is what we would consider to be like a survey course of Calculus 1. We are not going to get into hardcore mathematical definitions of what we call the delta epsilon precise definition of closeness. You just have to believe that there is a way to do it so that we can all agree what we mean by close, all right? For now, we'll use close as a very vague term and hope that we all understand. All right, here's a different function. This is an example of a piecewise function. Good. So it's a different function on different pieces of its domain. And I've intentionally made this so that it's going to behave very much like the one before. As you come in from the left side, still approaching the value 2. As I come in from the left, what's the value approaching? It looks like it's going to 8, doesn't it? But if I come in from the right, what happens? It goes up to 5 or so, and then it's coming back down. And it looks like it's getting closer to what? It looks like it's getting closer to 4 as I move in. So look, both the left and right sides, my x values were both approaching 2, weren't they? One from the left, one from the right. When I came in from the left on this piecewise function, my function was headed towards 8. When I came in from the, would I say right? From the left, the function was headed to 8. From the right, the function was headed to what? 4. 2 different values. In the previous example, it was the same value, wasn't it? It makes sense. If we have a jump there in the graph, then what happens coming from the left and the right are different. Yes? So I draw a new one for you. Hold on. I forgot to talk about something here. I forgot to ask you the college algebra question. What is f of 2? What's the actual function's value at 2? It's 8. Because the solid dot, right? The solid dot means it's defined there. The open circle on this one means that at 2, you're not here, you're up there. And the one above this, I forgot to point that out also. What was the function's value at 8 here? I mean, sorry, at 2. It was 8, because it's a solid dot there, right? So the college algebra question asks what's happening at the value. The calculus question is asking what's happening as you get close to that value. Another picture. So what I've done is I've taken the graph that we just looked at, but I took that solid dot away and I placed it right in the middle. What happens is I come in from the left. As I approach the x value of 2 still, what happens is I come in from the left? Where's it headed? It's still headed towards 8, right? Still headed towards 8. As I come in from the right side, where's it headed? It's still headed towards 4. What's the function's value at 2? 6. So coming from the left is different than coming from the right, and at 2, it's totally different from all of them, from both left and right. Now I want to look at a function, this function at 2 again. Okay, at 2, not negative 2, at 2. So I intentionally put a hole there, but if you were to graph this on your calculator, you would not see that hole, because your graph does not, your calculators do not do a good job of representing holes in graphs. It would look like a nice smooth graph to you. But I'm telling you there's a hole there. Why is there a hole there? It's undefined at 2? Because if you try and plug 2 in here, 2 squared minus 4, that's 0. You get division by 0. So that's part of that implied domain that's taken out. So is it possible for me to plug 2 into this? Can I plug 2 into this? No. The function is undefined at 2. Do you all agree? This is a very important problem, all right? Because we have a function that at 2, it is undefined. But if I try and approach 2 from the left, tell me about the value of the function. Where is it headed? Isn't the purple the y value? Okay, I'm trying to get close to that hole, but as I get closer, the y value seems to be getting closer to, it's not 0. Looks like, yeah, negative, that's as close as my program that I wrote will allow me to go. It looks like negative 0.25. Can I actually ever be 2? Or can I actually place it at 2? No. But do you agree that it still looks like it's behaving a certain way? Like you wouldn't say like, oh, it's headed towards 10. I mean, it's obvious that there's something it's headed towards. And same thing with the other side. If I come in from the right side, look at the value. The value here is in black. It's above, 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 above. Let me get closer and let me take the other one out of there. Does that look like it's getting? I went to 2. Okay, what happened at 2? That's a problem in my code. Don't worry about it. All right, so what does it look like? As I'm really close to 2, but a little bit to the right. The value is negative 0.24999. On the other side, we were, what, pretty close to that also, right? Yes? So at the end of the day, what we're saying is that this function, even though plugging in 2 causes a problem, we can still get meaning out of what it meant to be close to 2. And this is what I was trying to tell you last class. I said that calculus is about trying to get around the problem where you ever have something like that happening, where you're trying to find the rate of something at an instant in time. We said rise over run, there's no rise, no run. So 0 over 0, well then we throw it out the door? No. Maybe there's a way. Look, if I try and plug 2 into this function, what do I get on top?
0.
What do I get on bottom?
0.
0. But it makes sense that I could get, I get an idea of what's happening near 2, right? Near 2, that ratio is getting really close to negative 0.25. So there's some meaning there. Discuss the behavior of this function around the value x equals 0. So I'd like for us to look at this. I want you to look at the x value of x equals 0 and tell me what's happening. Let's see here. I'm going to call on, let's see, I've done those tables. How about anyone from Bailey, Josh table, this table here? Anyone there? Want to tell me what's happening? And just in layman's, just in layman's terms, talk to me. Tell me what you think about the behavior of this function around x equals 0. It's getting closer to 1. That's right. If you look at this function, here's 0 on the x-axis. What happens if you plug 0 in? We have a hole. And that makes sense. You can't plug 0 into this. But near 0, what is it doing? It's approaching 1. From the left side, it looks like it's approaching 1. From the right side, it's approaching 1. So even though it's undefined at 0, still has some geometric meaning near 0. Everything I've done so far, I've aided our thinking of this with pictures. The problem is that what we're going to do, everything that we'll do, we won't have the picture. We will have to do it algebraically, figure out these answers, which will be a little more challenging. But we want to have an idea of what it is going on, right? Okay, what about this one? What's the behavior of this around 0? And we'll go to back corner table. Anyone at that table? And you get the hard one. What you can't see here, because there's limitations to the computer, well, I'll zoom in. I did build it into the program. I can zoom in. We're looking right now between -1 and 1. Sorry, -2 and 2. And I want to know what's happening near 0, okay? Let me zoom in. Okay, so I zoomed in. So all that squiggly stuff that you saw is actually more squiggly. And if I zoom in even more, all of those squigglies are even more squigglies inside there. So what's happening near 0? Try plugging 0 in. What's wrong with just plugging 0 in right here? It's division by 0. It's undefined. So we know this function at 0, it's undefined. Near 0, it's oscillating. It's going nuts, isn't it? Yeah. It's going nuts. Now let's think about why it's going nuts. And this is a very deep thought. I think it's very deep. What does a sine function do? What do we know sine functions do? They oscillate, right? But they have a period, don't they? Isn't that period always going to be, what's the period thing? If you have like sine of ax, isn't it something like, doesn't it have to do with something here? Yeah, remember hearing that? Amplitude is how tall it is. Remember this? No? 2 pi over b. Well, yes, I could have used b here. You take the number in front of x, and you divide that number into 2 pi, and that's your period. That's how long it takes for it to do one cycle. So if the number in front of this is 1, then the period is what? 2 pi. But if the number in front of this is 2, it's what? Pi. And 3, and it's getting smaller and smaller, right? So what happens is, as the number in front of in here gets bigger, right? As this number gets bigger, the period becomes smaller or shorter. So looking back at this, what I'm trying to get you to see is that as x goes to 0, I want to know what happens to that ratio. I know you can't plug 0 in. We've already said that. You cannot plug 0 in. But what happens to the ratio if I have a a number that's staying the same and the denominator is getting smaller? What does that fraction do? It gets big, right? So what's happening is in here, you have sine of like infinity. So what, what you're doing is x is trying to get closer, right? Closer and closer to 0. As you do that, you're forcing this sine function to oscillate over infinity, meaning it's got to oscillate the same number of times as it does all the way across the number line. So it's moving in, it's like, okay, I'm oscillating. As I get closer, I've got to oscillate faster. I've got to get more periods in a smaller amount of space. And as I get closer, it's freaking going crazy is what it's doing, right? So what is the behavior? I'm still at that table. What is the behavior of this function as x goes to 0? How do you think we answer that question? It goes nuts, exactly. So we have a more technical name for that. We would say something like, what? That would be specific. I'm saying if you're looking at a function and it's behaving erratically as you're approaching a point, then we're going to somehow say that where it's headed to is like undefined, isn't it? You can't say that this thing is headed towards 0, can you? You can't say that the function is diving into 0. You can't say it's headed to 1, because as soon as you say it's up at 1, it's down at -1. You can't say it's 1 or -1, because at any point in time it could be in the middle. It's just never anywhere. It's always jumping back and forth. So it's like it doesn't exist, right? It doesn't exist. At 0, it's undefined. But as you move towards 0, it still doesn't make any sense. So this is a really strange example of really erratic behavior. Okay, I'm pretty much out of time. Yeah, we'll call it here. You can look at that and tell there's something going on as we go to 0. What is for homework? The take-home quiz, right? You've got to do that. And then...
Watch the quiz video for 1.3.
Yeah. How much more of that video is there? I've gone through a lot of this. There's not much left here. Well, it didn't look like there was much left there. Yeah, let's do that as the homework. I'm going to want you to do the take-home quiz. And then watch video for 1.3. And you can watch it from the beginning, but we stopped at 1.3.8. That's where I kind of ended. So if you want to pick up from there on the video, you can. Be ready for a quiz.
Due on Wednesday, right?
No, didn't we fix that? Did we fix that on the calendar? Hold on. No one mentioned that. Shit.
Yeah, Monday's Labor Day.
Not this Monday. Hold on. Didn't I send an email about this or no? Okay, look. I made a calendar the week before school started, and I said that Monday the 31st was a holiday. And then I realized Monday is not a holiday, so I fixed it. The calendar online should reflect it being fixed. We do have class on Monday. It's the following Monday, the 7th, I believe, that we do not have class. All right? So on Monday, the 31st, we should turn in your take-home quiz. You should have watched this video and be prepared for a quiz in class. Like come in and take a quiz over stuff we've talked about. Could be anything. Okay? Have a good weekend, everyone.
I just wanted to make sure you knew I was officially in the class.
Are you now?
Yes.
Okay. I had a feeling.